Okay, I guess we can go ahead with the talk now. Tom, thanks for accepting our invitation for your talk, and please feel free to go ahead and share your screen.
Thank you, Warren, for introduction and invitation, and glad to be here to talk to you about the MinXSS CubeSats. And as Bob gave a great introduction to a lot of CubeSat work that's being done at University of Colorado, this is just one example of some of the CubeSat work that Bob mentioned, but I'll go, of course, into more details about the MinXSS CubeSat. The acronym is pronounced like the animal minx. It stands for Miniature X-Ray Solar Spectrometer. And as Sissy Lynn mentioned, she's worked with us on solar measurements. We've been doing solar measurements, solar radiance primarily, to study effects on climate change as well as space weather effects for decades here at University of Colorado. I'll give an introduction to kind of highlights of the whole mission, the CubeSat technology, science, and future plans, and then I'll kind of dive a little bit deeper in each of those depending on how time is going. And I won't go over all the details of this slide. This is talking about CubeSats as disruptive technology. The National Academy of Science report, National Research Council report in 2016 came out talking about achieving science with CubeSats, thinking inside the box. And one of the introductory chapters was about how CubeSats are disruptive technology, kind of like iPhones are disruptive to communication systems. And I won't go over the details. Bob did a great job contrasting students versus professional. And to some degree, that's part of this, the reason why CubeSats are considered disruptive technology. Students can get involved. They bring a lot of innovation and excitement and creative ideas. They're lower cost, so it's more affordable as a student project. Even high school students are building CubeSats. And with so much that's been developed over the past 20 years, you can buy a lot of the components. So therefore, if you want to do a science mission, you can buy the spacecraft components and focus just on the science instrument or the payload part of it. And that's kind of some of the message that I think Bob was talking about as well. And it's also been seed for new businesses. A lot of the engineers have left CU and started their own business around some of the technology related to spacecraft technology. And the class sizes don't have to be large. We're finding that a class of 10 is an adequate size class to start up a project. And to go a little bit more specific into the MinXSS mission, it started a little bit of a history lesson here, I guess. Started in 2012, so almost 9 years ago. But it wasn't about the sun. It was about the far ultraviolet emissions of the thermosphere, basically the aurora at the poles. The student project defined a nice 3U CubeSat, but we never tried to propose it because it wasn't feasible from a data volume point of view. To do the science, you really needed a lot of data that you couldn't do with UHF communication. With today's technology, with S-band and X-band and other options, you could do a FUV, and we have one pending proposal from LAST to do that. But in 2012, we were only using UHF communication, 9600 baud type communication. So it just wasn't enough to send down images at the high enough rate that you would want to do science. So we kind of restructured the next year to focus on the solar X-rays. And you'll see in a couple slides some of the motivation of how the thermosphere, ionosphere, and X-rays kind of overlap. And we call this the Miniature X-Ray Solar Spectrometer. We submitted a proposal initially to the National Science Foundation. That was not accepted. We submitted the following year to NASA when they first had a science call for CubeSats, and that was selected. I think partly because we had the classes and had developed the concept fairly maturely. And here's a list of the scientists who have been working on MinXSS. These are funded people. So these are scientists primarily at LASP, Laboratory for Atmospheric and Space Physics, in the Aerospace Engineering Science Department. Amir is now at Southwest Research Institute, and Harry Warren's is at Naval Research Lab, and Stan Solomon's at NCAR, HAO, High Altitude Observatory. We've also had 4 graduate students who have been working on this project for several years. 2 have already graduated with their PhD. Chris Moore is now at Harvard Smithsonian. James Mason had gone to Goddard, but is now back at CU Boulder with LASP, but he's also planning to move soon to be at Johns Hopkins University. We got two students right now working on their PhD, hoping to finish up this year. So it's a small team as far as funded. This is mostly a student project, about $1 million per CubeSat. But it's not really a small team if you look at all the people that worked on it. So this is the list of all the students, professionals who's actually touched hardware for me. So it's about 80 people total. And that's typical of building a small satellite. This is, as you'll see, and you've heard, there's a lot of subsystems on a CubeSat, same number of subsystems as on a big satellite. So there's a lot of people involved with different levels of expertise. These are not just scientists or engineers. Some of these are more technical and business related and stuff. So there's a lot of people that go into building even a CubeSat. It was mostly developed as a class project. At the end, though, we hired some students to work over the summer and finish the build. And that kind of goes into addressing how do you get continuity with the students. So one of the things Bob mentioned is, every semester or every academic year, you get new students, you kind of have to retrain them. The design changes with each batch of students. So kind of after 2 years of this, we kind of froze the design and said, okay, we're not going to have any more classes. We're just going to build the last design. And we hired students to finish that design and build the hardware. And I have to give a lot of credit to the NSF Colorado Space Weather Experiment that Chinlin Lee and Scott Palo led for CU. That was flown in 2011, and that really made, or started in 2011, that made a huge difference for us because they provided the training of how to train students to do CubeSats, as well as a lot of the components that we use in MinX. Even though we changed a lot of it, a lot of the concepts and mission operations, the ground station, things like that, we inherited from CCSWE. So that having an existing program really helps to kickstart a new program. And our focus for these missions have been science. There's a lot of CubeSats are developed for technology or just as education. Both the CSWE as well as the MinX was very focused on the science. So therefore, we focus a lot on the instrument and the science that we'll do with those instruments. If you kind of look at the context of where MinX was launched in this history of CubeSats, this is Schwarzschild's chart of all the CubeSats launched every year. Of course, it started about 2000 with Cal Poly and Stanford defining the CubeSat standard or form factor, the 1 unit or 1U type size, about 10 centimeters by 10 centimeters. And in itself, I have to give them a lot of credit for leading the way for science CubeSats. A lot of people back in the early 2000s were saying CubeSats are just toys. They're not really to do any science. They're just an educational tool or technology demonstration. And there was a lot of technology demonstrations flown by NASA, but they had no plans until 2014 to do any science with CubeSats. So NSF started a science CubeSat program in 2008. We were fortunate at CU to get one of those, as I mentioned, Chinlin Lee and Scott Palo led. And then MinX was actually the first science CubeSat flown for NASA. Now there's a lot of science CubeSats from NASA as well. And there's approximately 100 CubeSats launched per year now. So there's a lot being flown. Some of it's commercial. Obviously, you probably know about Planet Lab type stuff, as well as the science that we're doing from university type CubeSats, as well as NASA centers and other programs. Just a quick overview of MinX1. It was launched on the Atlas V to go to the space station. So we docked the space station a few days after being launched. And then they went into a very long period. This was a nanoracks deployment. So that means there's a 1x6U deployer, and there was 2 3U CubeSats in each deployer, or for most of them anyway. But there was a interesting fight between the Japanese and the NASA agencies on who would launch first. There were some Japanese satellites and there were some US satellites. The Japan controlled the robotic arm to release the satellites, and of course NASA runs the space station. So there was a long fight. Instead of being deployed a few days later like we were told we would be deployed, it went on for 6 months. And finally, Japan won. They released their satellites first, and then we got released a few days later. And here's a picture that an astronaut took from the bay of the space station, watching the nanoracks deploying 2 satellites. One is MinX from University of Colorado. One is Xray from the University of Michigan. And then the next click should show you, it's not a movie, but it's a series of pictures taken very quickly of the deployment. Let's see, it's not playing. Start the motion. So this is kind of one of the first things we saw after deployment, is watching these 2 deploy. And it's very satisfying to know that your satellite's actually deployed and that they didn't come out and do any weird spinning or panels fly open in, unexpectedly. So that's great launching from the space station so you can get pictures like that. What really scared us though was this last picture looks like it's heading to Earth and it was only going to be in orbit for 5 minutes. Of course, it didn't. It really went into orbit about 400 kilometers, but this picture makes it look like it's heading straight to Earth. A little bit on the technology highlights. I'm not going to go over all the technology on MinX just because there's several subsystems, but some of the key technology that made this interesting mission, and a mission that's possible. One is, as already mentioned, the attitude control system for Blue Canyon Technologies. That really revolutionized solar measurements. This provides a few arc-second pointing on the sun, similar to our bigger satellites. And this was the first Xray unit flown for Blue Canyon. So they, of course, were heavily excited to have us launch and get this flight demonstration for them. They were great supporting this and have built wonderful systems, as many of you are flying or planning to fly. The other interesting technology is the Xray spectrometer from Amtech called X123. As you can see, it's a handheld X-ray spectrometer. We, of course, modified it so it could be in space, but basically we're flying their basic unit. And then a third thing that we did for kind of technology testing was 3D printed parts. We did in metal parts. This is not plastic 3D printing. This is called sintering, where they kind of lay down a metal powder and then run a laser to melt the powder. We made some deployment hinges in stainless steel. That was very successful. And we also made the housing for one of our instruments called solar position sensor out of aluminum. Both are shown there in the pictures. So the students got to play with designing and making 3D printed parts that worked out very well. And a little bit on science highlights. I'll go a little bit more into the technology and science highlights more, but just giving you a quick overview now. The science is is focused on understanding how the solar X-ray affects Earth's ionosphere and thermosphere. I know that overlaps a lot with Lauren's and others' research there on the ionosphere. And part of that is also understanding the flares, how many flares, how much energy is in a flare, as well as the active regions on the sun that creates the flares. The MinX1 was able to observe more than 100 flares. Kind of the middle figure shows MinX time series is green, and the GOES X-ray sensor, which is kind of one of the standard broadband measurements. MinX is measuring spectra. The GOES XRS is measuring a broadband time series of flares, showing that there's lots of flares just in a few days. And then another interesting aspect is taking some of these spectra and making more detailed reference spectra for the soft X-rays as well as EUV. And I'll show an example of that. And the example shown there is for a differential emission measure, D&M. We also, because we're spectra that overlap with XRS, we also provided a calibration for the GOES XRS time series as well. And one of our highlights is that we won the 2016 Small Set Mission of the Year award. I think that was largely because of James Mason, who socialized MinX and really went out there and recruited votes. I don't know if you can see my cursor or not, but there's James Mason there in the middle. He was one of our few students that actually was in all of the student classes, and he, being in so many different student classes, he had many hats. One semester he was an instrument scientist, one semester he was system engineer, one semester he was program manager, one semester he was thermal engineer, and he of course helped us with the ground stations and stuff. So he being part of the program for so long, he got to see all aspects of the MinX CubeSat and is still involved with MinX. So thanks to James and many other students who made this mission possible. MinX2, after MinX1 had re-entered, that was in being from space station, you're at 400 kilometers. You only can expect to stay up for about a year before you get dragged down by atmospheric drag. We didn't have any propulsion, so MinX1 ended essentially a year later after being deployed. We decided to write another NASA proposal to extend MinX science to look at active region evolution. That got launched with several delays along the way, but it got launched in December 2018. This was into a sun synchronous orbit. Because we had all the experience from MinX1, MinX1 took about a month to commission. MinX2 only took 4 days to commission. So we were taking core science measurements a few days after we launched. We did have a problem with MinX2. We had SD cards on MinX1 and 2, and we had a single event upset about a month later in January 2019. We have been unsuccessful to recover from that event for the SD card. It was related to a Watchdog timer that was set for a few seconds. In hindsight, it should have been set for minutes. We could have recovered the mission if the Watchdog timer was minutes long instead of seconds long. And if we had a more robust RAID tolerant memory storage that all the last CubeSats now have. We do have a very successful month of mission of measuring the quiet sun spectrum, so we still consider MinX2 successful, not as long as we wished it to be though. And we're still listening to see if MinX2 recovers, but we're not expecting it to at this point. And then MinX3 really was an opportunity to be on the InspireSat satellite that was mentioned already, and Lauren, of course, is very familiar with, and I guess many of you there as well. We came up with an improved version of the spectrometer that I put in parentheses MinX3, but because it's slightly different technology, the students, Bennett and Robert shown there, renamed it the Dual Zone Aperture X-Ray Solar Spectrometer, or DAX. This DAX flew on a sounding rocket for a NASA calibration in June 2018. and showing the solar spectrum from that rocket flight, showing all the different solar lines in the corona, as well as the Brimstall and Continuum for a typical solar spectrum. We're really excited about this higher energy resolution instrument. We're really excited to get that flown on InspireSat that's supposed to launch next month. As I think maybe already mentioned, InspireSat 1's been delivered to India and is ready to integrate soon. So this is kind of the overview slides. I don't know, I'm glad to pause here and take a few questions. My other slides are more details about the technology and science. I don't know, Lauren, if you want to entertain questions now, or if you want me to just keep going, or.
Sure. If you so we've had a few questions in the chat. First of all, a question from Sam Huang. Why would you want to use 3D printing to manufacture the solar panel hinges? Is that for a mass issue?
It was because it was such a complicated part. You got cylinders and rectangles and moving parts. It's moving parts that have to integrate very delicately with the brass part. So it was really decided to do it because it was too complicated for the students to machine.
Okay. Okay, Sam, do you want to turn on your mic?
Yes, I'm Sam Huang, and yes, but I think the hinge can also be very simple, because I think the 3D printer, they also have some crack issue. Do you also test your hinge for the mechanical test?
Yes, I agree. The 3D printing in metal is weaker than if you machine it from core metals. It's usually about 70% strength that you normally would get if you machine it traditionally. We did some analysis as well as structural tests and deployment testing to verify the 3D printed hinges wouldn't crack or break. And we did aluminum housing as well. The company we used did not like using aluminum, and I can see why. After we made them, they're very porous and very rough. If you stay with harder metals like stainless or titanium, 3D printing comes out pretty nice and smooth, much better than aluminum 3D printing. So in hindsight, 3D printing in stainless is a pretty good product, but it is weaker than traditional machining.
Okay, thank you.
Okay, I had a question a little more about the Watchdog Timer issue. So I'm kind of curious why increasing the Watchdog Timer would have allowed for recovery, if you could elaborate on that.
Yeah, so the way the software was written in Minx, and it probably has been changed for your generation of satellites, but the way the Watchdog Timer and the SD card initialization was written for Minx, if the software in initialization could not find the SD card, it would check like 1,000 times, are you there, are you there, are you there, for the SD card. And that loop to check for it took I think 45 seconds in hindsight. We didn't realize how long it took until hindsight, but whereas the Watchdog Timer was set for like 35 seconds. So before it could get out of this sort of not infinite, but a long loop to check for the SD card, it would get rebooted by the Watchdog Timer and start that 1,000 time check for the SD card before it reached its timeout. If we had a longer Watchdog Timer, which in hindsight, we're recommending people set it for like 5 minutes or something, that initialization for the SD card would have timed out and the program would have run normally. And we just would not have had a SD card, and we could have had a mission with just downlinking real-time data.
Okay, thank you. That's a very important lesson learned. And you mentioned using rad-tolerant flash. So are you guys still using SD cards for later missions, or have you moved to some other type of storage medium?
No, we're not using SD cards anymore. We're using just flash memory. There's, I guess, NAND and NOR type technology, but several of them are more red hard than, some are red hard, some are just red tolerant. To keep costs down and delivery times down, we tend to just use the red tolerant version, although a few missions have used the red hard version. But they're very similar technology at SD card in the sense that they're flash, but it's just more at the core level of flash that's more reliable.
Okay, thanks. One more question from Christian. Christian, can you turn on your mic?
Of course. Thanks, Tom. I wonder, have you guys not considered things like phase change memory, for example? I mean, at this point in time, that would be available. Say, for example, from Intel, you can buy a couple of Optane modules and strip the chips from there and then fly radiation hard by technology.
Yeah, I don't know if LASP is exploring that or not. Bob Marshall actually might be able to answer that better than I. Rick Conner's the one to really answer that, but I don't know if they're exploring those options or not. I know they're using more traditional flash, just not in the SD card variety.
Okay, thanks.
Okay, thanks to everyone who asked questions. I think we can move on now.
Okay. So the next few slides are a little bit more details about the technology. You already kind of had an overview. I won't speak to this because you saw this slide already, but like any large spacecraft, CubeSats have all the same subsystems as a larger satellite. Payload, your instruments, pointing, your attitude control, I call it phone home, your communication, your radio, power, your processor to control the data flow, and propulsion. Now, MinX did not have any propulsion, but some satellites do. There's the NASA Small Satellite Technology State-of-the-Art document that's online. They originally promised they would update that every year. They're not updating it every year, so it's a little bit outdated, but it's a great place to get started if you never worked with CubeSats, to look at all the many options of subsystems you can buy. It's really quite remarkable how many are out there now. Here's a more detailed exploded view of MinX and all the boards and stuff. I'll go a little bit over this just to kind of highlight what was student built versus what was purchased. The command and data handling, the CDH, the processor, that was student built. It was partially based on the CCSWE CDH. The electrical power system also inherited. What was different is we bought the Azure Space solar cells so that they would be glass covered and be basically more robust, more stable in space. And then the students assembled those cells onto a panel. And we bought the SparkFun lithium polymer batteries, which was the same heritage battery from CCSWE. The communication, we bought that from Astrodev, the Lithium 1 UHF radio. We did have problems with that getting upset in space a few times during the mission, like every 2 months it would get upset. The way to clear it is to turn it off and turn it back on. The attitude control system, we bought that from Blue Canyon. Wonderful system. I'll show a little bit more of that in a minute. And then one of the instruments that the students built was the solar position sensor, Xray sensor, that had some heritage from the GOES satellite, but the students built the boards and assembled and tested everything. And then we bought the Amtech Xray spectrometer called X123 with some modifications that we made ourselves to make it space ready. So the blue is what was purchased and the black is what is student built. So about half and half. And as Bob Marshall talked about, there's trades you're always making, but the more you can buy for the spacecraft system, the more you can focus on the science payload. So here's the two pictures of the instruments, the X123 on the left and the solar position sensor and X-ray photometer on the right. And again, that housing is 3D printed in aluminum. And the two technologies that really made MinX a success, one is the X-ray spectrometer. This provided high energy spectral measurements. We've been making broadband measurements for decades, but we don't have the spectral energy measurements that we really need to study the sun in this energy range. And then, as we already mentioned, the exact or pointing system, achieving better than 10 arc-second stability with one star tracker. If you get 2 star trackers, you can get about 3 arc-second precision stability. So amazing system for something that's only a half U size. And same for the Amtech unit, it's less than a half U in size. Excuse me. MinX1 being the first one to fly exact, of course, got to demonstrate its capabilities. Here's a couple example plots. The left plot is in the safe mode when it's not trying to do precise pointing, just trying to find the sun. Its requirement or goal was 10 degrees, and we show in our actual flights it's better than 3 degrees in safe mode. This is not doing the precision tracking with the star tracker, just using magnetic fields and inertia unit information. And then on the right is a science where they're using the star tracker to tell it where it's pointing in space, and then trying to control in 3 axes to look at the sun. And being in the sun synchronous, or not being in sun synchronous orbit, being in low Earth orbit on the space station, we have about 60 minutes of observation and about 30 minutes of eclipse. So that's why the data shows the gap there. And then you also notice spikes kind of not quite halfway, but doing the orbit. This is related to when the star tracker becomes occulted, either by the moon or Earth, and therefore it has to do a roll maneuver. And while it's making that roll maneuver to find stars again, the pointing's not as good. And that's only for like a few seconds per orbit. So it's really a minor impact. In the ground stations, we inherited the one from CSWE that's on last roof, the top left picture. We also, because MinX2 was going to be in sun synchronous orbit, we put one at the University of Alaska in Fairbanks in 2017, so we could have 2 ground stations. And we've been using a backup ground station from our expert that helps us with communication, Jim White, has a ground station south of Denver in Parker, Colorado. And a significant fraction, probably more than 10% of our data, is from ham radio operators. So wonderful, wonderful set of community providing data. Now these are beacons, they're not necessarily the core science data, but as far as getting a lot of data of engineering quality of where the satellite is, voltages and currents, and some science data, the ham radio operators have been quite amazing at collecting data and sending it to us. The next few slides, it's about the science. And I already shown this slide, so I'll skip this. One of our motivation is to understand the energy from the sun deposited into Earth's atmosphere, and kind of going from right to left, the visible and infrared, make it to the ground, as well as scatter off of clouds. And as you go to shorter wavelengths, it gets absorbed higher up in the atmosphere. The thermosphere, the extreme ultraviolet, is responsible for a lot of the heating. But as you get to the shorter X-rays, it penetrates deeper because the atmospheric cross sections are smaller. And so the X-rays are really important for getting deeper in the atmosphere, and because they're so energetic, they can ionize the atmosphere. So they're a large contribution to creation of the ionosphere. So our motivation was to study the E region part of the ionosphere that was least understood. And for that, we needed the X-ray measurement. So that was kind of our underlying motivation. Also, several of the people involved with this were solar scientists as myself. So we're interested in measuring this X-ray spectrum as well. Another motivation is there's been a gap in the soft X-ray measurements for spectra. At the longer wavelengths, the top part of this plot, we have SDO Eve measuring a large part of this spectrum above 6 nanometers. And then at the shortest wavelengths, we've had a lot of missions to study below 1 nanometer, but above about a half a nanometer, there just hasn't been measurements. So we don't have spectral. We have broadband measurements, but not spectral measurements. And when you look at the sun, example there in the right, bottom right, unlike the visible sun that looks kind of like a nice image with a couple dark sunspots, in the X-rays, all you see is mostly the active regions and the loops from those active regions that you see in the corona part of the sun. And one of the interesting aspects is, here's an example spectrum, or 2 spectra in the top left. They have the same magnitude of energy from 0 to 7 nanometers, but one is from a flare and one is from an active region. They have the same amount of energy, but because the spectral shape is so different, the bottom figure shows where that energy is absorbed in Earth's atmosphere, and they're separated in peaks by about 5 kilometers, which is about a scale height. So that was one of our motivations, is that we didn't know, just by measuring broadband, the energy 0 to 7 nanometers, we couldn't tell you what spectral shape was the right one to use for atmosphere modeling. So we wanted to measure the spectrum. And here's an example where we did measure the spectrum and was modeled by Stan Solomon using his NCAR TIE GCM model to show how flares are deposited in the atmosphere. Again, a focus has been on the E region enhancements down around 100 kilometers. And another motivation from a solar physics point of view is in the soft X-rays, there's a peak predicted around 1 to 2 nanometers, kind of shown there in the purple circle there. And as you look in the spectrum in the bottom right, it's decreasing in irradiance as you go to shorter wavelengths, kind of the Planck continuum, then with a lot of emission lines shown there, like the hydrogen Lyman alpha there at 121 nanometers. And one of the interesting predictions from Eric Rogers from using timed XPS data was that the 1 to 2 nanometer peak there, kind of shown there in purple, would be as bright as that bright Lyman alpha emission. And this is a log scale in irradiance. So we really wanted to measure this spectrum to see where this peak energy would really truly come out of. So we built the MinX satellite, we launched it, we got hundreds of spectra. We're still analyzing those data. I've got several papers out as well. And again, here's an example time series showing the MinX integrated spectrum. We get individual spectra for each green diamond, but just comparing that to the GOES time series, just showing you how many flares are possible in a day. And here's a more detailed look at the spectrum from just one flare. This is one of the brighter flares that flared from a active region on the sun. The green spectrum in the top right is pre-flare, what the spectrum looked like before the solar flare started, and then the black one is kind of near the flare peak. And the bottom right shows you the time series of the integrated X123 signal, again showing you the flare irradiance or pre-flare irradiance fairly constant, and then a sudden rise by about a factor of 50. The eclipse period that we don't observe the flare is shown there in the gray. Again, that's a disadvantage of being in Leo. We get solar eclipse or orbit eclipse, every 95 minutes. And some of the science that we're looking at from a solar physics point of view is looking at the temperature of the flares and how hot it is, as well as looking at the composition changes during a flare. I don't really have a lot of time to go into all those details, but that's kind of at a very high level. What we're looking at from a physics point of view is looking at these temperature changes. A typical corona is 1 or 2 million Kelvin before flare, but during a flare, it's like 10 to 15 million Kelvin. As well as the composition is changing during a flare. Shown kind of here, the green is the corona abundance, which is decreasing, and it goes into the physics of how a flare generates magnetic reconnection in the corona. It accelerates particles down to the photosphere, and then that evaporation from the photosphere injects new mass into the coronal loops, and that lowers the abundance factor relative to hydrogen and helium. So that decrease at the flare peak is related to that heating in the photosphere, chromosphere. The other kind of science that we're working on is reference spectra to help with atmosphere modeling. Because we don't measure all the time, we also want to have proxy models of the solar spectrum. And one way of getting that is through this what's called differential emission measure, where you measure, or not measure, you model the temperature versus the emission measure as a function of temperature. The previous, before MinX launch, is shown there as the square symbols and diamond symbols for quiet sun and active region. Some new results from MinX, as well as the rocket dikes. Shown here is a rocket dikes where you fit a Gaussian in temperature. You can't see it because it's overlying the top of all those Gaussians, but there's a black line that describes the envelope of all those Gaussians. And you can see that it doesn't agree with either the Chianti, quiet sun, or active region reference D&M. So we have new results on what active region D&M looks like. When you model this, what's important for us is for SDO-Eve, we measure this black spectrum above 6 nanometers. And with MinX or DAX, we're measuring below 1 to 2 nanometers, but we don't have any spectral measurement between 2 and 6 nanometers. By doing the differential emission measure fit with these spectra, we're able to model what that spectra should be in that gap. So that's the exciting new stuff, is predicting what those spectra should be based on SDO measurements and MinX spectra. And the kind of final thing about science is space weather. Now, this maybe is more operational than science, but one of the things, the GOES XRS, which measures 0.1 to 0.8 nanometers, or 1 to 8 angstroms, which is this very broad line shown here. That's their broadband measurement. They need a calibration, or can benefit from a calibration. Instruments get launched, they can degrade in space. So this provides a calibration check, as well as improvements to the irradiance knowledge for these broadband measurements. So the MinX spectra are the ones shown there, with a large variation. The GOES is just the bandwidth shown at an irradiance level. And the result for comparing to XRS-B to MinX is shown here, showing that it agrees well with their predicted calibration, the red line, at the high C and M class, but as you get to the B and A class X-ray irradiance, their calibration needed significant adjustment. So they've worked on improving that, and I think if you go grab their data now, you wouldn't see this comparison. It would be more flat now. And our future plans, just kind of a quick summary of what I've already said. We're waiting for MinX 3 on InspireSat 1, hoping to launch soon. And Amal, who's a PI for InspireSat 1, has a paper about the mission. Interesting. It's focused on the ionosphere as well as the solar X-rays, which is exactly the science we were interested in for MinX. What's interesting, this is a larger satellite, so it has the NCU's ionosphere instrument called the Compact Ionospheric Probe, SIP, that's also on board. So we'll take time doing this satellite at night, take ionosphere measurements, on the day side of the orbit, take solar measurements. So very complementary measurements. As well as we're collaborating with the Indian group on their similar type measurements on their solar X-ray monitor that's in space now, and hopefully will overlap in time. A couple more satellites that are pending. We've gone through phase A studies with NASA. One's called Cubics, that Amir Caspi is PI, to do solar X-ray imaging. So that's obviously needs the S-band technology. And then Sunset doing EUV imaging as well as chronomass ejections from the EUV images, and that's with James Mason as the PI. So again, being imagers, they need to have that high rate S-band. And my final slide here is about a summary saying basically what you've heard already. We've demonstrated key technology, we've measured hundreds of flares, and here's a list of several papers that are kind of good starting points for if you want to read about it. Also, you can find all these papers and more on our website there. So thank you for your attention.
Okay, thanks a lot, Tom. So I have a couple of questions. So I think it's very interesting that in the case of MinX, you guys used a commercial off-the-shelf spectrometer for the payload. And so I was wondering what the qualification process was for this COTS component that was not originally designed for use in space.
So we took the whole system apart. We prepared all the electronics with conformal coating and staking, and we put in some thermal foam to get the heat out to the case. We did vacuum testing. We flew it on the sounding rocket 2 or 3 times before we ever posed it to fly it on CubeSat. So we spent a fair amount of time just playing with the instrument in the lab to verify it could go into vacuum and not overheat. And it's cool. It's really a quite amazing instrument because it has a thermoelectric cooler that cools down to 240 Kelvin. So it gets it down to very, very low noise measurement. So it's a really quite remarkable little instrument. And because it's has all those great qualities, we wanted to see if we could make it space qualified by just simple changes to it.
Okay, thank you. So let's see, we have a question from Cece. Cece, you need to unmute yourself.
Yep, sorry. Hi, Tom. Thank you for the talk. Quick question about MinX science when it's compared to GOES Xray mission, Xray irradiance. So is it truncated because MinX is measuring the spectrum? Is it truncated and integrated to compare with GOES?
I'll just go back to this plot here. So the MinX Spectra starts here at about a half keV or about 2 nanometers. It goes down. Now we actually go out to 20 keV, but you can see we're photon limited out here around 10 keV or about 0.1 nanometer. So basically there's just not any solar photons to be seen. The GOES bands, this is the B band, is basically 0.1 to 0.8 nanometer band, and now GOES A is shorter wavelength. So we don't really measure the photons at these shortest wavelengths or higher energies just because there's just not enough photons to measure. So most of the signal from GOES is really from these photons at the high end of their band. So that's where most of their signal is coming from anyway. I don't know if I answer your question or.
Well, I think no. Yes, I think it goes without saying that just different spectrum, different part of the solar spectrum, the variety of different part of the solar spectrum varies differently during strong solar activities, just as you pointed out earlier. So when we see the evolution during a solar flare, you do see the range of the dynamic range of the irradiance change differently with 2 instruments. Thanks, Tom.
Okay, so what are the plans? So for MinX 3, what are the plans for further improvements to the to both the spacecraft and also the scientific objectives?
So MinX 3 has the DAX instrument, which has the highest energy resolution spectrometer we've ever have flown. So we're really looking at this more solar lines to study. Also, by having multiple missions, we can look at how the active regions evolve, the solar active regions evolve over time. MinX 1 was a 1-year mission doing the declining phase of solar cycle 24. We're now entering the rising phase of solar cycle 25. So InspireSat 1 will hopefully show us a different phase of the sun as well. So that's kind of the difference or complementary parts of having multiple missions.
Does anyone else have any additional questions? You can either just speak up or type it in the chat. Okay. Looks like it was a very comprehensive talk, and no one has any additional questions. So, thank you very much, Tom, for really good overview of MinX and DAX. Looks like space qualifying that spectrometer's really paid off.
Yeah, and others are using it too. I mean, there's probably 3 other CubeSats planning to fly that pretty much the same thing. So we're going to have potentially several of them in space over the next couple of years. Well,
looking forward to the new results, and all the best with, well, I guess to everyone involved with InspireSat-1 on the upcoming launch.
And yourself too, itself. And,
Okay, thanks a lot. Okay, thank you, Tom, and thanks to everyone for tuning in. Hope to see you next time, and hope you all have a good day, or night in Tom's case.